Pain is a critical protective sensation that warns us against harm from infection, cancer, and the environmental forces. In doing so, it overrides other sensory and cognitive systems to urgently focus our attention on real or impending danger. But pain can also outlive its usefulness as an acute and beneficial warning system and instead become persistent and debilitating, distracting us from life's daily pleasures and activities and significantly diminishing our quality of life. Indeed, chronic pain remains a major unmet medical need and widespread public health issue affecting millions of people throughout the world. The societal toll is further compounded by the overdependence on morphine and other opiate analgesics, with their attendant side effects and potential for abuse. Pain is also a complex physiological and behavioral response that engages the nervous system at many levels, from sensory nerve endings in the skin to emotional centers deep within the brain. Better strategies for assessing and treating pain require a deeper understanding of the basic biological mechanisms underlying the detection, transmission, and processing of pain signals at each stage along the pathway. This is a shared goal of scientists and clinicians throughout the world, including many friends and colleagues here in Spain. My own group has focused largely on the first step in pain sensation, whereby noxious signals from our bodies or the environment are initially detected by sensory nerve endings in the skin or other tissues, including muscle, bones, or the gut. But what types of molecules enable nerve fibers to respond to physical factors such as heat and cold, or to chemical irritants such as acid? And if such molecules exist, how are their properties altered following physiologic insults such as inflammation or nerve damage that promote chronic pain? Answers to these questions emerged in part from my own long-term fascination with what one might call chemical neuroethology, or the study of how evolution and behavior converge to enable the discovery and use of natural products for culinary, spiritual, or medicinal purposes. Of course, exploiting natural products to uncover new molecules and signaling pathways is not unique to our work, and this approach has already played an outsized role in the pain world by yielding two of the most widely used classes of analgesic drugs, namely morphine from opium poppies and salicylate or aspirin from the willow bark. Taking inspiration from these examples and from classic physiologic studies of Jansko Gabor in Hungary and Hensel and Zoderman in Sweden, we asked two simple questions. One, what specific molecular mechanisms enable us to appreciate the pungent heat of chili peppers or the refreshing coolness of mint? And two, how do such mechanisms relate to our normal sensations of temperature and pain? Answers to these questions led to the discovery of heat and cold activated ion channels, called TRPV1 and TRPM8 respectively, providing a unique molecular toehold into deciphering the neural logic of thermal sensation, nociception, and pain, while validating the sensory nerve fiber as a rational and selective target for novel analgesic drugs. This exciting journey of discovery, with its unanticipated forays into new territory, including chemical, structure, and physiological and behavioral areas, has been traveled in partnership with many exceptional trainees and collaborators who brought their own unique talents, insights, and creativity to the group dynamic. Watching students and fellows develop their scientific persona and then move on to forge their own independent careers has been a thrill all its own and a daily reminder of the guidance and support that I received from my own mentors along the way. In fact, heading an academic research group is something of a Shangri-La existence, in which the continuous matriculation of energetic trainees keeps an aging mentor like myself intellectually youthful, curious, and ready for new challenges. I'm enormously grateful to members of my lab, past and present, for this amazing gift and for their contributions to all that we have accomplished together. The other great engine of discovery has been public financing of research, which in my case has come from the U.S. National Institutes of Health and the University of California. Bedrock support from these institutions, together with contributions from dedicated philanthropies, has allowed us to follow our dreams and curiosity, even when there was no guarantee that a practical outcome would emerge. But as we have seen time and again, this is how so many of the most impactful and unanticipated scientific breakthroughs are made. I'm proud to be associated with institutions such as these that support intellectual freedom and creativity in the pursuit of fact-based thinking, discovery, and decision-making. In closing, I would like to thank the BBVA Foundation and the Selection Committee for recognizing somatosensation and pain as a significant and prize-worthy area of research. I am pleased to share this moment with Ardem Patapoutian, whose beautiful work on mechanosensation has provided complementary and critical insight into the biology of touch and pain sensation. Beyond our groups, I am indebted to the many friends and colleagues around the world who share their insights, ideas, reagents, and passion for research with the hope that our collective discoveries will help alleviate suffering from chronic pain and other debilitating disorders.